Let's sketch the following polynomial curve. Well, we can find the y-intercept by setting x equals 0, and then differentiating the function with respect to x. Well, what we get is x cubed minus 6x squared plus 8x, and then setting the derivative to 0, and factorizing this expression, we get x by x minus 2 by x minus 4. So therefore, we're going to have critical points at x equals 0, x equals 2, and x equals 4. And if you sub these x values in this equation, well, what you're going to get is y of 0 is equal to 3, y of 2 is equal to 7, and y of 4 is equal to 3. So that's our critical points. And you can go further by taking the second derivative to determine if each of these critical points are concave up or concave down. But we're going to take a guess that they look something like this, because this is a cubic function. Let's sketch the following curve. So if we set x equals to 0, we get y is equal to negative 2. And if we set y is equal to 0, then we get the following equation. And therefore, solving for x, we get x is equal to 1 plus or minus 3 root 3. So x is going to be around 6 and minus 4. And if we take the derivative, well, what we get is 2/3 by x minus 1 to the negative 1/3. And therefore, we can see that there's going to be a critical point at x equals 1 because the derivative is not defined. And if you substitute x equals 1 into this equation, you're going to get y is negative 3. So that's our critical point. So our curve is going to look something like this, with a cusp at this point. And you can take the second derivative to verify that the curve is concave down on both sides. Let's sketch the following curve. So if we take x equals 0, we're going to get y is equal to negative 3. And if we take the limit as x approaches 2 from the left hand side, so that's going to evaluate to minus infinity. And as x approaches 2 from the right hand side, this evaluates to positive infinity. So we have an asymptote at x equals 2. And if we also take the limit as x goes to infinity, then y is going to go to 0. So we have an asymptote at y equals 0 also. So the curve looks something like this. Let's sketch the following curve. So setting x equals 0, we're going to get 6 on 4 or 3 on 2. And if we take the limit as x goes to 2 from the left hand side, well, y is going to approach infinity. And as x approaches 2 from the right hand side, y is also going to go to infinity. So therefore, we have an asymptote at 2. And if we also take the limit as x goes to infinity, and also as x goes to minus infinity, then y is going to go to 0. So our curve looks something like this. Let's sketch the following curve. So y of 0 is equal to 0. So that's our first point on the curve. And if we take the limit as x approaches 2 from the right hand side, well, what we'd get is plus infinity. And as x approaches 2 from the left hand side, we get minus infinity. So we can draw in our asymptote at x equals 2. And now if we take the limit as x goes to infinity, and also as x goes to minus infinity, well, what we'd get is 6. So we have a horizontal asymptote at y equals 6. And now we can plot our curve. Let's sketch the following curve. So y of 0 is 1/4. So that's the y-intercept. And if we set y equals 0, then x equals 1. So we have the x-intercept at 1. And now if we take the limit as x goes to -2 from the left and right, then y approaches infinity. So we have an asymptote at -2. And if we take the limit as x approaches infinity, then y approaches 1. So we have an asymptote at y equals 1. And now taking the derivative, using the quotient rule, you're going to get 6 by x minus 1 on x plus 2 cubed. And setting this to 0, we get a critical point at x equals 1. And y of 1, as we saw, is 0. So this here is our critical point. So therefore the curve must pass through the y-axis, turn around at 1, and asymptote to y equals 1. And on this side it asymptotes to x equals -2. And on this side, the curve approaches both asymptotes. Let's sketch the following curve. So because the degree of the polynomial in the numerator is larger than that in the denominator, we use long division to put the equation in this form. And the y-intercept is at -5/2. So that's our first point on the curve. And as x approaches infinity, the curve's going to approach this straight line, because this term becomes dominant. And that's our oblique asymptote, which is a straight line through y equals 2. And now as x approaches 2, then we get an asymptote at 2. And now if we take the derivative, that gives 1 minus 9 on x minus 2 squared. And if we set the derivative to 0, our critical points are at x equals -1 and x equals 5. And then substituting back into our original equation, we get the following y values. So our critical points are somewhere around here. And our curve looks something like this. Let's sketch the following curve. So because the degree of the polynomial in the numerator is greater than that in the denominator, we're going to get an oblique asymptote. And we can use polynomial long division to write the equation in this form. So when x equals 0, y is equal to 0. So that's our first point. And when x equals 1, y is also equal to 0. So that's another point on the curve here. Now we can see that we have a removable discontinuity at x equals 1. So we can draw in our circle here. And when x goes to infinity, the curve approaches this straight line which passes through y equals -2. So that's our oblique asymptote. And when x approaches -1, we have a vertical asymptote at x equals -1. And then differentiating this function, what we get is 1 -2 on x plus 1 squared. And then setting the derivative to 0, you get the critical points, which are somewhere here. So the curve looks something like this. Let's sketch the following absolute value curve. So the speed is the magnitude of the velocity. And v of 0 is equal to 2. And when v equals 0, we can factorize the equation. So we get t minus 2, t minus 1. So these are our x-intercepts at 1 and 2. And then differentiating the velocity, that gives us 2t minus 3. And setting this to 0, we have a critical point at 1.5. So our critical point is around minus 0.3. And then taking a second derivative, you're going to get a positive value. So our critical point is a minimum. So our curve looks something like this. And because we're taking the absolute value, then this is our actual curve here for the speed, which is a magnitude of the velocity. Given the graph of the derivative, let's sketch the graph for the function f of x from x equals 0 to 4. And we're given a few values of x here, which we'll plot on a graph. So initially the derivative is positive and decreasing, so the slope of the tangent to the curve for the function is positive and decreasing. And then at x equals 1 we have a critical point, so a change in direction. And somewhere here, the slope of the tangent to the derivative is 0, or the second derivative is 0, so we have an inflection point or a change in curvature. And the derivative is 0 at x equals 2, so we have a critical point, so a change in direction. And then somewhere here we have an inflection point, because the second derivative is 0, so we have a change in curvature. And at x equals 3 we have a critical point, so we have a change in direction. And at this value of x, which is around 3.5, we have an inflection point, so a change in curvature. And this is our rough sketch of the graph of f of x. Given the first derivative of a twice differentiable function, evaluated at the discrete points given in this table, we're asked to determine if the function is increasing or decreasing over the interval from 1 to 5. And I've plotted the points here for visualization. So because the function is twice differentiable, then it has a second derivative. So the first derivative must be continuous, and it can look like this, for example. And you can get infinitely many curves like this. So therefore, given the derivative can be positive or negative, then we don't know if it's increasing or decreasing over the interval. I'll just write don't know. And is the function concave up or concave down over the interval? So again, we only know that the derivative is positive at these discrete points. So we can't conclude whether the function is concave up or concave down. It can be both. So to obtain a second derivative, we have the slope of the tangent to the first derivative, which is different at different points. So we can't conclude that the function is either concave up or concave down. Now part C asks us, what is the second derivative evaluated at a value c, given the average rate of change of the derivative in the interval is equal to its instantaneous rate of change at x equals c. Well, here we can use the mean value theorem and apply it to the second derivative. So that's equal to the first derivative evaluated at x equals 5 minus f dash of 1 over 5 minus 1. So that gives us the slope of the secant of the derivative over the interval. So if we substitute f dash of 5, we get 3 minus f dash of 1 over 5 minus 1. And that gives minus 7 on 4.